So like I was saying, so last week we started machine learning, I said support vector machine under our important clarification series. So try to bring out or to itemize some of the important facts and features to take note about support vector machine. Just like any other machine learning algorithm, it has its own advantages, and especially very strong when the dimensionality of the data set is a little bit large, especially when you have more features than usual. So we've always seen that support vector machine try to achieve exceptional result where others are not have that kind of capability. However, we have always made us to realize that in machine learning, there is no one algorithm solves all problem. No. So every algorithm has its own challenges. And there's no algorithm that is always better in all situations. So that is going to be contradictory to the principle of machine learning, which we always say that let the data speak. It's very important. So the performance of an algorithm will be determined to a large extent on the nature of the data set you are having. And that's why you have to check out different machine learning algorithms on your data set to be able to know which one is going to work for you. Now, because each data set comes with their own unique attributes, hidden information that you are not aware as human being, we cannot see them physically. However, machine learning algorithms have that capability of have insight into those data sets and then bringing out useful patterns, useful information that could possibly benefit us in our day-to-day activity. So last week we ran through some of those unique features, like saying that support vector machine is relatively new. It was built on the principle of statistical learning theory. And also we did mention that it makes use of the principle of searching for separating hyperplane or to make the decision boundary. It also will have a belief that you can always draw a separating hyperplane between your two classes. So, and if it's not able to draw that hyperplane at some normal level, it tries to explore that, oh, maybe this data is hard, try to push it to a higher level. So it keep pushing it to a higher dimensional level until it's able to draw a line, a separating hyperplane between two classes. So what this should communicate to us immediately is it means support vector machine directly only work for two classes. When you have two classes, it can work directly on it. However, if we have multiple classes, is it not going to be able to solve that? Then it's hard to solve that problem in an indirect way, which we are going to describe later on as we proceed on this exposition on support vector machine. So we did summarize this, and we're going to be bringing them up, that the complexity of trained classifier is characterized by the number of support vectors. It has a couple of stuff we call support vectors. These are going to be the representative data points that will be taken over towards the prediction process. When we want to do validation or testing sets, these are the representative value we will be bringing in to represent the entire data set. And so that's one of the reasons why it is unique. So in terms of computational complexity on the testing set or validation set is very low, because we are not going to be using the entire data samples, but rather we are going to be using just selected samples, which we call support vectors. So we did also mention some of the unique applications and a host of others. We specifically dealt with this because it's very important to have that general philosophy of support vector machine. So whereby you draw a line, this is a line drawn. See, we can see that this line is having small margin. It means we could draw a better line with large margin. You see, the philosophy is trying to draw a separating line between your two classes, but make it as large as possible. See, this is a line. If I draw this line, I keep pushing it back, pushing back here, I push it back this side. Once it touches one of the sample here, I have to stop pushing. Once it touches here, I have to stop pushing. So this one is going to become the support vector. This also is another support vector from this side. So as the case may be. Now, so however, for the second one here, we can see, so it's a maximum margin. You try to check it out. So it touches here, here. It's also touching this. These are the support vector. The same data point. Because there are a lot of possibility of drawing. I might want to draw my own line like this. See, somebody might want to draw his own line like this. But then this is going to be a bad margin because it's going to be very low before it touches this. So we want a line that we can push back as much as possible before we start touching any of the support vector representative values. So this is what we call the large margin. Once we're able to get large margin, this is the unique. It means you're going to pick up these support vectors as the representative value for your data set. And then you can move on to the classification stage, the predictive stage, to be able to check, okay, if a new sample comes in, we are going to be in need of this support vector to determine the new sample that is coming in, is it supposed to be to this side or is it supposed to be in this side? So, which is how it's actually works. So with that support vector machine, the support vector now will be a very unique aspect of the philosophy of support vector machine to be carried out towards the prediction process. So we also clarify the issue of linearly separable and non-linearly separable cases. See that there are some problems at a go, you can easily separate them. No issue. Like this is a class, this is another class. SVM want to classify this into two. It needs a separating hyperplane. It can easily separate them. Just draw a line. Expand it until it touches the first one here, expand it until it touches here, and then you finish your task. However, sometimes the data set is just too hard. We did mention this last time. So in which case, look at the class. This is one class. This is another class. Member of this class is also here. Red. This is class A. There's another class A members. They are not together. And then this is class B. So we want a line to be drawn between them to separate. There's no way you can draw a line in this case. So we need to do something. And that is the unique power that support vector machine brought to the table in what we call the kernel function. That's why some people, they do refer to support vector machine as kernel machine. See, because with that kernel, a lot of unique capability could be actually brought up with support vector machine, and a unique outcome could be achieved. So when you have very hard data, then in that case, it is believed that you can push your data to become two-dimensional. Like this data is on the same line. This is just one x-axis. Can we introduce y-axis to it to make it two-dimension? See, this is one dimension. We brought in y, become two-dimension. Then we just say that my y is equal to x squared. It means for every value of x, square it and assign it to y. Square it and assign it to y. For every value of x, square and assign it to y, you can then see here. Now, so once we pick this y, this value x, we can scale it. You can see here, if you scale this one, it raises a little bit. This is 2. 2 will be higher than 1. 4 will be higher than this. When you keep scaling, the farther away from the 0 point, the larger the value. Let's say this is like 16. If you scale 16, you are going to have higher value of y here. That's why this one goes up. For the negative side also, you have to make the squaring. You have to square it also. But because when you scale negative, everything becomes positive. That's why it doesn't go down. It doesn't go to the y scale. For -1 square is going to be 1. Minus 2 square is going to be 4, and then it goes on like that. So when you do this is known as the kernel function now for this problem. You can see here, we are able to draw a line between this system. You can see here, we draw a line between them successfully. And then we can push back the hyperplane until it touches. This is going to be the support vector. This is going to be the support vector. So this is the unique way that support vector machine is able to solve problem both linear and non-linear. Because sometimes you don't even know if your data is linear or not linear. So support vector machine has that capability to solve either linear or non-linear for you. Because it's always believed that if you push your data to the appropriate high dimension, it will become separable. This is a very unique principle. Even sometimes at second dimension, it might not work. You might have to introduce the third dimension, three-dimensional data plane. At that point, you are going to see other example later on. And I did give, I give example that last week, a practical real-life example of how you can visualize support vector machine. I said it is like you have a set of students in your class. For the linearly separable case, you want to classify them into tall student and short student. So by just looking at someone, you can just say stand up, look at someone, you can be able to know that, oh, this person is short, this one is tall. It's very easy to do. We don't need to do anything more. The maximum thing is to take your measurement and just measure the person if you have to do that. In most cases, you don't even need to do that. Mere looking at someone, you know that, oh, this person is going to be tall, and no one will argue with you. Such problem is referred to as linearly separable case, a very simple case that the data set is presented in such a way that it could be easily identified and separated. However, there are situations that you cannot do that. And I give an example like if someone wants to separate a soul student into those that can run marathon and those that cannot run. Can you just ask your student to stand up and you look at someone and say, hey, it's him, you cannot run. You can run. You don't do that because you may be making a very wrong assumption that some people you think that physically they might not have the stamina, they might actually be the one that will win the race. In such a case, we say that this is an example of non-linearly separable case like this. You cannot differentiate who is who. What do? You subject them to kernel function. And what is your kernel function in this example? You ask your student to run from building A to building B. Maybe between those two buildings, like 3 kilometers in between. Run from one point to another point, and then you return. And we are going to put a timer there. Anyone that return within that time limit, he can run. Those who could not return before that time limit, they cannot run. You know, we have to do something to be able to differentiate between who can run and who cannot run. That thing we have done is the kernel function implementation for those set of problems. And after finishing the race, you don't need to, no one will argue with you because some people will not be able to make it back. Ambulance, you have to be on the way. Some people might not be able, they might need the help of paramedics to be able to make it back to their station because 3-kilometer race is not a fun. It's not everybody that can make it. At the end of the day, you are going to know that, oh, these people, they can run marathon. This one cannot run marathon. This is exactly the example we gave that in real life, how support vector machine is able to push everyone to get separated. And every problem, at a point in time, the data will become separable. Initially, everybody is mixed together. You cannot tell who can run, who cannot run. But by subjecting them to this simple test, you are able to do that. That is the principle of kernel trick. People call it kernel trick that support vector machine do employ to solve classification problem. And by extension, we are going to talk about regression problem also later on. So we discussed this last week, and I think that was where we stopped. So we are going to now continue to look at how is the margin drawn. See, the margins and the support vectors. See, here, you can see here, someone decided to draw this margin. This is a data set we want to decide if a student should buy a computer or should not buy a computer. We used this example before in some of our earlier explanation of classification problems. So we can check out some of our earlier videos on this. So in this problem, someone can decide to draw this line because there are a lot of possibility for the lines you can draw. How do you draw the appropriate margin? This is mathematical, actually. So somebody decide to draw this. You can see here is going to have only one support vector here and another support vector from this side, because you must have support vector from both sides of the classes. And then you draw you try to maximize it. You can see here we got a small margin. This is because of the choice. What if I make my own draw to be like this? See, you can see here, look at another possibility. When you draw it, you draw this line, you try to expand it back, you are able to get this support vector. This is a large margin. So there are lots of possibilities you can have. I might decide to make my own to be like this. You might decide to make your own to be like this. But no matter what you have selected, when we start to push it back, before touching, until they touch one of the sample from both sides, do they create a large margin? Because we call support vector machine maximum, we call it maximum margin classifier. Another name for it, maximum margin. So we are looking for the maximum margin, and there's a way you can actually determine that. So that's why we say support vector brought to the table on the first one-dimensional, that the example we gave, on the two-dimensional, it could actually have to go to even three-dimensional, as the case may be. So now, so once you have your data, you have different possibility here. Then you have to look at, okay, what are we going to draw? Which kind of margin are we going to be in it? So the support vector machine takes the data point and output the hyperplane, which in two dimensions is a simple line. However, in higher dimension, it becomes like a plane, hyperplane. So, and this line is going to represent the decision boundary upon which we are going to base our future predictive solution on. It means we are going to store our support vectors, and based on those support vectors, we are going to be able to decide what is the class of new samples that we are going to get. To remind us quickly, when we are doing machine learning training and testing, the idea is we want to create a model that inductive learning hypothesis states that if it works on enough data, it will work on unseen data. If it works on enough training data, then it will work on new samples. So what we are trying to do is we want to train a model that we will show the model, the training set, and the outcome of the training set, and we want it to be able to come out with an appropriate separating hyperplane. So, and that model, once we pick the support vectors are going to be part of the model we have built. Very important aspect of it, because we will need them to be able to decide. Then when new sample comes, then we are going to say, hey, which side do you belong to? Is it to side A or to side B? Based on the affinity or the closeness to those support vectors. So a lot of effort have been made in making the support vector. Yeah, indeed. So like I said, there are many possible separating hyperplanes or separating lines you can draw. So it depends on the way you are viewing it. And that is the equation of that particular plot. With this equation, you can actually draw as many lines as you can. So the hypersurface equation is given, of course, as this one. So when mathematically inclined, so you have possible options. Look at it. So if you select the wrong option, you end up with the wrong system. That's why we look for the one that can generate maximum margin for us. If you get the one with maximum margin, then you can be sure that subsequent model you are going to build will be something that is going to be accurate. Now, identify the hyperplane. That is, identify the hyperplane. So we have the plus one representing the x and the minus one representing the class naught. So a zero means above the hyperplane. Yeah. So which means if you're talking of zero, one is going to be plus, another one is going to be minus. There's a plus class, there's a negative class, yes or no. And then Zero means somebody is still sitting on the hyperplane. That's a sample that is sitting on the hyperplane. So the idea is that we want to avoid a situation whereby any sample is going to be sitting on that hyperplane. So you plot each feature as a point in n-dimensional space and then build hyperplane as the case. Excuse me. Yeah. Now, so you build the hyperplane with the maximum margin. This is very, very important. Like I was saying, you build the hyperplane with the maximum margin. So the SVM is the one that maximizes the margin from both tags, from both sides, trying to maximize the margin. So a hyperplane is a linear decision surface that splits the space into two parts in binary classifier. So one of the limitations of support vector machine is it can only deal with binary classes. That is, class that has two classes. That is, sorry, classification problem that deal with two classes only. Is it going to pass exam or is it not going to pass? What grade are you going to get? Is it A or B? It cannot deal with A, B, C at the same time. However, if you have more than one classes, then we can use a special SVM to do that. Either you try to do A, B, we call it 1 versus 1, 1 against 1 SVM, A or B or C, or A or C. It means if I want to separate A, B, C classes, I have to train at least 3 SVM here, AB, BC, and then AC. It means you pick 2 by 2. Or I use 1 against all. 1 against all means, okay, I'm going to have A against BC. I'm going to assume B and C are one class. They belong to one class. And I'll separate A from them. The next, I'm going to train B against AC. And then next one, I'm going to assume C against AB. This is a kind of indirect way of using support vector machine to solve classification problem when you have multiple classes, because SVM is only able to solve for binary classes. Why? Because it's only able to draw a line between 2 sets of classes. So you cannot treat 3 at a time, 4, 5, 6. But it doesn't mean it cannot work for multiple classes. Of course, we clarified for ourselves in the past, the more the number of classes you have, the more challenging the modeling is going to be. So that's why sometimes, even apart from the SVM limitation of dealing with only 2 classes, sometimes when you have complicated problem, it's always better to formulate it as binary classes, and later you can combine your result in using ensemble and some other areas we're going to be discussing later on. Now, so then the hyperplane is a linear decision survey that split the space into 2 parts in binary classifier. So, and there will never be any data point inside the margin. The idea is in this inside the margin, there's not going to be a particular data point that you can find inside such. So how does it work? The first thing is to identify the right hyperplane. If we choose the wrong hyperplane, that could actually spell challenge for the system, as we hear. You see the equation is there, well split out. So here it's got to, it means it's staying on the top of the hyperplane. We don't want to have it, this case. Then this one is the second case. So these are the 3 possibilities, but this one, we try as much as possible not to have it. Of course, we have a special SVM later on when we introduce slack variables. We won't go on to that one for now to avoid confusion. So identify the right hyperplane. We select the hyperplane which segregate the 2 classes better. We have to look at what is the hyperplane that will separate it better. And then once we are able to do that, then we maximize the distance between the nearest data points of either class. That is, we maximize the margin, as we described. Once we maximize the margin, you stop when it touches samples from both sides, from both classes. And those are what we refer to as the support vector, as the case may be. So we say, imagine a separation of line to the closest class point. See, separation of line to the closest. So we keep pushing the line. Look at this one now. So we can say this is a good margin. That is a little bit more of equidistance as far as possible for both sides. You draw this line. When you push it back, it's more or less something of equidistance. It's not too close to these classes. So to this class, sorry, it's also not too close to the other class. It's in between them. This is a good margin. But this is a very bad margin. You see, very close to the blue class. You can see it's almost touching these samples. It's not very too much far from the other class. This is not going to generate a fair model for you. We don't want this kind of. So we want something that's a little bit equidistant. So that's why when you are positioning it, we have to check out, and that is what the work of those hyperparameters we are going to talk about them later. How hyperparameter will determine, because you are not going to be using your hand to check where should I put the system, where should I put this line. There are hyperparameters that will determine how the margin is going to be. So we have to set those values appropriately. We'll talk about that one later on. Now, once you select the appropriate margin, then you are actually good to go. So now, we mentioned when the data is linearly separable, things are very easier for us. When it's linearly separable, things are very, very easier. So you just draw the appropriate margin, as the case may be. So for the linearly separable case, so here, let's say we have let the data D be the X1, Y1. This is the input, this is the output, up to the maximum value you have, all your samples. This is your mathematical definition, where XI is the set of training tuples. Training tuples means you have X1, X2, X3. Let's say we have 3 features, and then the Y is the label. We have Y here. So for every value of input, you have the outputs. This is the definition we are providing. So there are infinite lines, that is hyperplanes, separating the two classes, but we want to find the best one, the one that minimizes classification error on unseen data. This is what we want to do when it comes to drawing the hyperplane, because there are a lot of possibilities. I showed this one to us earlier. Let me repeat it again. You can see this case. See, your hyperplane, you can decide to make it like this. It could be this one, it could be this one, it could be this one. You have so much possibility. So this is the point we are making here. So since you have so much possibility, infinite line actually is infinite. There's no limit to the number of lines that we can draw to separate the class. However, we are looking for the one that is going to the most maximizable one, which is going to minimize the classification error. Because the closer you make them together, the easier that this one might conflict with allocating to this one. Now, so SVM searches for the hyperplane with the largest margin, that is the maximum margin hyperplane. Another name they do call support vector machine classifier is maximum margin hyperplane, MMH. Always looking for that. Once you are able to get the maximum margin, you are done. So once that is done, so the separating hyperplane, as we mentioned, could be written thus. Of course, there are a lot of mathematical background on it. So this is the separating hyperplane. It could be written as equal to 0. Then we're going to have the +1 horn and then the -1 horn. So where W is the weight vector and B is scalar bias. So the weight are attached to X. X is your input, and then the bias is there. For 2D, we can have it. For the hyperplane, then we can make it even more, H1 and then H2 as the case may be. So any training tuple that fall on hyperplane, H1 and H2, or the side defining, they are called the support vector. This is what we theoretically talking about, what we have just shown us diagrammatically or pictorially. So once you have the H1, is the first side of separating hyperplane and the second side. Then you move them apart until they touch, each of them touches the samples from either side. And that point we call the support vectors, and they're very important. And this becomes the constraint for complex, that is the convex quadratic optimization problem we want to solve. So in support vector machine, it has a very strong mathematical background. So you have to do the quadratic optimization, objective optimization, and the linear constraint that is placed upon it. And then the quadratic programming, Lagrangian multipliers, and also software source will come in. You don't need to, for now, you don't need to bother yourself with all these high mathematical stuff. The mathematician will take care of that. So, and you don't need to do that before you can use your support vector machine. This is just to let us have an insight into what is actually going on. So, support vector machine is one of the machine learning algorithms that has very strong mathematical background, actually. So, once we are dealing with the margin, this is how this is the formula to be able to determine the distance from the object to the hyperplane. So, because like I said, you are not going to be working in a pictorial form. We just make it pictorial to make you understand what is going on, but actually it will be done mathematically. So the support vectors, which are the closest object to the hyperplane, will be taken care of. And the margin also, with this equation, we can take care of the margin, which we already mentioned this also, and this case, and the case of when it's equal to 0, where we want to avoid having any sample in this particular location. So we said the linear SVM mathematically, we have the +1 prediction zone. It means when new sample comes, whatever falls into this side is going to be predicted as positive class, and whatever comes to this side is going to be made to be negative class, hoping that no one falls in between, as the case may be. So we treated this, and then as the case actually may be. So that's the maximum margin, and then this is the M. You can do the simple calculation. So this is how the binary linear classifier actually works. Now, so this is the binary linear classifier for SVM. That is how the simple thing actually it works. The simple way of working it out, or as the case may be. Yeah. I think we made mentions of something similar to this earlier. So the classification margin, we deal with those mathematical stuffs. Yeah, as the case may be. And then once we identify your support vector, the specific one, then the model is built appropriately with the one with the maximum margin. So in summary, linear SVM classifier can be mathematically stated that assuming all data is at least distant 1 from the hyperplane, so the following 2 constraints follow from a training set. So we have the training set tuple, the X, and then the output. As you know, this is supervised learning. So for support vector, we deal with this. And then the final formulation also, we can have some of the things we need to minimize this particular situation. So, and then which will lead to not to solve the optimization problem. So we say in most of the real application, we need to optimize a quadratic function subject to linear constraints. So, and the solution involves constructing a dual problem where the Lagrangian multiplier is associated with each constraint in a primary problem. So the mathematician, we understand better what we're talking about. So the primal form, you formulate the Lagrangian formulation, and then you're going to have the dual form, which we can state in a simple term. You are finding lambda to lambda n such that this unique formulation can be maximized under the constraint 1 and constraint 2. So this is the mathematical system that we want to solve for the SVM. And like I said, the good news is we don't need to solve this problem manually by ourselves. There are software that are already written solving this problem. We can use it without even having an ink of how the mathematics is solved. But for those who are mathematically inclined, we are invited to actually explore it further. More mathematicians can even come out with maybe better optimization techniques to be used. We can have people who might want to come up with even kernel functions that can be used that are better than the one that are presently being used. These are areas people can go into, especially people with mathematics and computer science background. They can work in this area. However, since I say one of the logo of our training is machine learning for all, for those people who are not mathematically oriented, you do need to worry yourself about those mathematics. You can still use your support vector machine successfully to solve your problem, to develop model, do your predictive solution for either your business application, use school problem solving, and any problem you want to apply machine learning to. Of course, you bear in mind that there are some mathematical background, but for now, you can ignore them for convenience, but it doesn't mean they don't exist. But not knowing those deep mathematical background does not mean you cannot use machine learning, because machine learning is for all, as I stated. So this is the problem we formulated, subject to this, and then the solution is given by this, where NS, you are submitting it together. NS is the support vector machine. You can see support vector. This is where I told you, the moment you get your support vector, it is done. You need those support vector to be able to do your prediction. That's why they are very, very important. If you choose a wrong support vector, the answers will always be wrong, because the final solution will be, after all your optimization, Lagrange multiplier, this and that, the final is going to be a single summation of based on the support vector machine you have gotten, and a wrong support vector machine will doom for the system, or as the case may be. So I believe this is what we're going to stop for the day. So next time we're going to look into non-linear support vector machine. So cases where support vector machine is non-linear, so what can we do about it? How can we solve those problems? And once again, why support vector machine is effective is one of the secret. It's support vector, especially when you have high dimensional data set. When your data set is huge in terms of features, the number of features are many, because it's going to make it to suffer from cost of dimensionality. So because the more the number of features, the more the number of samples you need. However, the number of samples are always limited in number, so making us to run into the problem of cost of dimensionality. Cost of dimensionality. We explained this concept earlier in our previous videos. We can check them out. So with support vector machine, we've used it a lot in a lot of our problem solving, especially material sciences, where we have very limited data sets. So they have been used successfully, and also for other areas. So we're going to go, this is where we're going to call it a day. Thank you very much for listening. So we're going to take a couple of questions before we leave. If you have any question, you can raise up your hand for recognition. Thank you very much, and I wish you all the best. Thank you.